All right. So we're going to go ahead and start looking at page 237. So we've been talking about these rational inequalities or rational functions. But what we're going to start talking about today is the introduction to rational functions with identifying restricted values, looking at the domain, x-intercepts, and y-intercepts. So the first one, simply what we're doing is we're taking this rational function and we're just plugging it in. So we want to show work for this. We know how to do this, but we're just going through the motions. So f of 0, we're plugging in 0 everywhere there is x to this original function up top. So once you finish the first one, you can check your answer up on the board. Then we're going to do the same thing for -2 and 3. So on the second one, when you get there and you get this answer, what kind of answer is this?
Undefined.
Okay, it is undefined. Undefined. But in terms of a graph, what is this going to look like on a graph? Okay, this one will be a vertical asymptote. So this is an important idea here. You're going to have a vertical asymptote if you get an answer, and you can write this down, that is some number divided by 0. That's when you get a vertical asymptote, when you get some number divided by 0. So 15 divided by 0, that's some number value divided by 0. Let's go ahead and try number 3 and look at its result, f of 3. When you get to number 3's answer, what kind of answer is this? We went over a few examples, I think, yesterday, or maybe it was Friday, when we had an answer like this. But this answer is what? It looks like it could be two different things, but we actually determined it is... Rebecca? It is undefined because we have 0 on the bottom. So it is undefined. So that is true, but now this one was a vertical asymptote. What do you think this looks like on a graph? Yeah, anytime we have a 0 over a 0, that will be a hole on the graph. So vertical asymptote is a number over 0, the hole was 0 over 0. And if you go back to the example from yesterday, I think we had a hole at -3 on the one graph that we used. And if you look at your equation, when we solved it, we had 0 over 0. So that puts a hole in the graph. Alright, so those 3 scenarios. You can just get a number value, so whatever your function is, a vertical asymptote, some number over 0, or a hole in your graph, 0 over 0. Now rewrite the function f of x in completely factored form. So we're just talking about this one up at the top. Go ahead and factor it in this box down here. Factor the top, factor the bottom. Was anybody able to factor the top yet? Anybody? Griffin, did you have any luck?
X minus 3 and 2x plus 1.
Yeah, 2x plus 1, x minus 3, thank you. What about the bottom? I think the bottom was a little easier. Yes, go ahead. Okay, x plus 2 and x minus 3, very good. So it's completely factored. Now we're going to use this factored form to kind of help us through the rest of this problem, maybe. Bless you.
Thank you.
So, next question about this factored form then. What do you notice about the result of 2 of the 3 function values above and the factored equation? So what do you notice about the results of 2 of the 3 function values above and the factored equation? What connection do you see from your answers up here and this factored equation? And I think it really just builds upon the idea that we talked about yesterday. So, maybe think, what do these values do to this factored form on the bottom?
Those values make the denominator 0.
Yeah, that's what I'm looking for. It makes the denominator equal to 0. So f of x was undefined at x equals negative 2 and x equals 3. And these values make the denominator equal to 0. Okay, very good. So if we were to plug in negative 2, that would make it 0 here. If we were to plug in 3 there, that would also make it 0. So we get undefined. So all of that should have been sort of a review. We should know how to plug in. We should be able to factor and determine what makes the denominator 0. Now we're going to talk about the definition of a restricted value. A restricted value, we're going to write down the formal definition, but it's going to be this value x, so some x on your function that has no y value. So the function's undefined at that x value. So a value of x for which there is no y value. The function is undefined at that x value. So a value of x which there's no y value, so there's no answer if you would plug in that x. The function is undefined, so the bottom would become 0 at that x value. So you don't have an answer. Kind of like these two up here. We plugged in negative 2, we had no answer. There was no y value. We plugged in 3, we got 0 on the bottom. There was no answer. So those are two of the restricted values. Alright, so it says the graph of f of x. And again, this is the same one we were dealing with from the top of the page. Is pictured to the right, so we have the graph here. Describe the graph of f of x at its two restricted values. So what's happening at the restricted values? That's what I want to know. We know it has 2. What's happening at each of them? Exactly. At x equals negative 2, there's a vertical asymptote. I'm just abbreviating. You can write it out if you want. VA. Vertical asymptote at x equals negative 2. And at x equals 3, there is a hole. So if you look at negative 2, there is your asymptote. And at 3, there's your hole. So those are the restricted values. So now when you think of those restricted values, they're going to ask for domain of your function. But remember, you're restricted. You have values that don't work within your domain. So now when they ask for the domain, we need the intervals of your domain. But think about your restricted values. So what would the domain of this function be? Remember, domain, x values. We go from negative infinity to what? Negative 2. Then from where to where? Negative 2 to 3. And lastly, we go from 3 to infinity. Now again, the reason we have to break this up is because at negative 2, we don't actually have a point. That's where the vertical asymptote is. And at 3, we don't have a point. That's where the hole is. So that can't be included in the domain. Any questions on the front side? All right, let's go ahead to the back. Marie, you still copying? Okay. Good? Okay. So on the back, what we're going to do, I'll read this first, then we can describe what I need. So study the graphs of the functions below. Clearly, one function is different from the other 3. Identify this function and state 5 ways that this function's graph is different from the other 3. So again, we want to look at these, we want to look at what's the same about them, what's different, and we're going to be able to make 5 statements. We're going to write out 5 statements up here on why that one graph differs from the other 3. So go ahead, take a minute. I'm going to give you a minute to analyze them, look at them, maybe jot down some ideas that you think could possibly be part of the 5 things that are different. So go ahead and take a minute. 3 are the same, 1 is different. Think about all the ideas you know about graphing. And remember, I'm not saying these graphs are exactly identical, but I'm saying the properties of 3 of them are the same, where the properties of the other one are different. Did they forget about the assemblies today? Alright, you may not have all the ideas yet, but maybe you have 1 or 2. What is one thing that you could see? Or let's first discuss which graph do you think is the one that has the different properties? Marie? Second one down, second one over. Yeah, so this one is the one that has the different properties. So we want to know what makes this one different from the properties of the other one. You have one here? Yeah, very good. H of x, which is this function here, they each have a different name. H of x has 2 vertical asymptotes. Again, I abbreviated that. Others have how many? The others have how many?
Excuse me, interrupted. We need all seniors report to the auditorium. That's all.
The others have
seniors
1.
Report to the auditorium. Thank you.
We are going to finish this page while you guys are at the assembly, just so you know. Okay. Alright, so h of x has 2 vertical asymptotes, the others only have 1. So that's the first statement. What else do we see? We talked about the vertical asymptote. Is there anything maybe about the horizontal? Anna?
One of the lines passes through the horizontal.
On which one? Which graph?
The h of x.
Yeah. So h of x crosses its horizontal asymptote while the others don't. So number 2, h of x crosses its horizontal asymptote while others don't. Okay. Very good. Alright, we have, actually we're going to write, I have 6 different things, so we have like 4 more things we can write about this. Marie?
The other ones have a whole discontinuity.
Have a what, sorry?
A whole discontinuity.
Okay, and h of x does not. So h of x does not have a whole. Okay. Very good. Go ahead.
An h of x, one of its lines is an array.
Is a what, sorry?
Is an array, like it has an endpoint on one end that continues on.
Let's see. Where do you see the endpoint at?
If it's
Oh, down here. Ooh. Are you looking here?
yeah, like that one.
Okay, so I think they may have technically forgotten to put it there. So if we see, this is an asymptote, right? So is it ever actually going to reach there? So this is actually just continuing on. It looks like it's right on the line, but it's just continuing on. It always gets closer and closer to an asymptote, but you never get on the asymptote, okay? So that is continuing on there. Okay. What else do you maybe see? There's one that's maybe, it could be obvious. Maybe you're overlooking it. There's one that's more simple.
It's 3 lines to 17.
Exactly, yes. So h of x has 3 pieces. Others have 2. Okay. 2 more things that I have. Marie?
H of x has all of the fruit.
Okay. I think you're heading in the right direction. Are you talking about here?
Yeah.
Okay, so we do need to discuss that, but we need to be a little more specific. You're on the right track. There's something about that we do need to state. If it's doing that, h of x has a what? A point of inflection. Does that sound familiar? Yeah, so it's from here, you're going to have a point of inflection somewhere in there. So h of x has a point of inflection. I abbreviated that, POI, point of inflection. The others don't. Okay. And one last thing. It might go back to the idea that Marie kind of mentioned when she was trying to figure out this one. She mentioned something about multiplicity. So it's not exactly multiplicities, but it has something to deal with that. This would be our last statement.
Well, has multiplied set intercepts.
Okay, so how many does it have?
2.
How many do the other ones have?
1.
Exactly. H of x has 2 zeros, but others have 1. So 2 zeros, or x-intercepts. Okay, I know we have a lot of time left, but the next page I think is important for everybody to be here to be able to go through that. I don't want to go through that without them here, because those are some major steps in being able to do some of the homework. And so if you want to take some time and try some of the homework with the ideas we've gone over, that would be some time to get started. You may not understand all of it or be able to do all of the homework at this point. You could ask some questions, but you may at least be able to get started and get part of it done. So use the rest of class time for that. That way everybody else doesn't get too far behind.